Okay, very good. So today we are going to do the paper by Hawking, where he derives Hawking radiation. So now the first thing we are going to do is just so I'll go through section 1 and 2 of the paper, and then jump to the very conclusions and discuss a little bit of the conclusions. That's the plan. So I'll skip section 3 and most of section 4. Okay, so first, of course, we are in a curved space-time, and particles exist, and we can kind of describe them, so it should not be the end of the world to describe particles in curved space-time. But at the time, people were starting to develop quantum field theory and understand quantum field theory. And of course, you could ask, does it make sense to have quantum field theory in curved space-time? Does it make sense to fix the space-time and then put quantum fields on top? Or do I need immediately to study back reaction? Why can I just study quantum field theory on a curve, on a space-time? Why can I do it instead of considering back reaction? Okay? So first he does an estimate to show, okay, indeed it's okay, we can do usual quantum field theory. So let's go through that estimate, which is quite cute and relatively simple. And so the claim, the point is that the notion of particle in some curve, especially what matters is more the fact that it's time-dependent background, is subtle, and it's subtle because to define particles we very much like the notion of positive and negative frequency, and positive and negative frequency is something hard to describe if things are time dependent, because what starts as a positive frequency could become a negative frequency and so on, right? So it's subtle, it's hard to define positive and negative frequencies. Now, how hard is it? Of course, if it's almost flat, it's almost time independent, it's almost easy to do, it's almost trivial. But if it's very curved, it's very time dependent, then it's very hard, right? So we have to try to quantify this a little bit. So Hawking says, suppose I have a region, and this is some curvature. So this is a typical length where the curvature changes. In other words, he says take a particle with some velocity v and build some kind of tetrad and try to consider the biggest possible curvature in some direction of this tetrad. So you construct some curvature R, A, B, C, D, the maximum in all possible directions, and this will define some 1 over this L curvature squared. Okay. Which is what he calls B. Okay. And now we have two possibilities here. I have some curvature radius, and now I could imagine some field whose frequency is such that here, this frequency, we would have some frequency omega much bigger than square root b, versus a different scenario where I have my particle, where I have myself, and I have some frequencies omega that could be of the order or smaller than this square root of b. Right? And the claim is that if we are in this situation, then here omega bigger than 0 versus omega smaller than 0 is okay with exponential accuracy of the type e to the minus some constant times omega square. Well, it must be over b. I'm a bit confused because I don't remember over b, but okay, I don't. Sorry, 1 second. Let me check that my definition of b is not 1 over b. Yeah, it's okay. Okay. So now, why is this true? Why is it true that if omega is very big, that it's exponentially small? This you can see with a simple toy model. So a toy model that illustrates this well is the following. Consider the following problem, where you have x dot dot plus omega square x equals 0. Right? Then you would say that this is just an oscillator, and this would have a solution x equal e to, for example, e to the minus I omega t. Now suppose instead this frequency depends on time, but it depends on a time in a slow way. It starts with omega, and then it slowly changes to some omega prime. Right? So changing slowly is like a big radius of curvature. Then the claim is that the solution will look like this at t going to minus infinity. So here the solution oscillates like this, and here, if you solve this differential equation with an omega like this, x would be e to the minus I omega prime t plus exponentially small terms times e to the plus I omega prime t. So you see that the two possible modes is plus minus omega t at plus and minus infinity. And if you start with minus and you change slowly, then the system changes adiabatically and stays in the same state all over, and when you are at the end, you are still in the negative frequency case. But not completely, because there is some time dependence. You get a little bit of positive frequency. So you get a little bit of particle production, but very, very small. Okay? So this would be a toy model where we would say very tiny particle production. Namely, I start with a field that has only negative frequency, and it evolves to a field that is almost again in the vacuum, but it has a little bit of particle production. Okay? On the other hand, if this frequency were to change very dramatically, then here I would have the two modes with order 1 coefficients. So here I start with negative frequency, and here I can have positive or negative frequency. It's more or less order 1. I don't know what I get at the end. And so in this situation here, we have order 1 ambiguity. In this situation, the frequency is of the same order as the typical curvature scale. So I really don't know at this order, for these frequencies, I don't know exactly whether I will have an ambiguity in what I call creation and annihilation operator. Okay? And so let's try to quantify the total uncertainty. So let's consider what would be the uncertainty in energy density. And Hawking writes the following formula, that my uncertainty, the fact that space-time is curved, I would say there are no particles, but actually things become ambiguous for some frequencies. And so I would say that what matters are the low frequencies. So I would integrate the omega up to something of order square root b. For those frequencies, the density of frequencies in 3 dimensions would be omega square. So this is because we are in 3 dimensions. And the energy of each of them will be the frequency omega. So this is the energy as function of omega. And so these scales like b squared, in other words, as 1 over L of curvature to the power 4. And you see that 1 over the curvature radius to the power 4 is much smaller than 1 over the curvature squared, for curvatures that are much, if this L curvature is much bigger than 1, and 1, if we put back the units, is n Planck. If we put back h bar and c. So for curvatures that are much bigger than the Planck length, then the quantum fields are okay, and I can fix the vector. Okay? So therefore, quantum field theory in curved space is okay, except at Big Bang and so on, when the curvature is very big. Right? Except when the curvature is very big, maybe singularities like Big Bang and so on, quantum field theory in curved space is very good. Okay, and so then the uncertainty, this is very small. But then he says, but this small effect could accumulate. I can have a very tiny effect over a very long time. Right? So, yes, the effect can be very small locally, so that quantum fields are perfect, are okay. But this tiny effect could accumulate. And he says, indeed, this would be like a spoiler. Black holes, he says in the introduction, radiate. So they look like they have some thermal temperature, and indeed this effect accumulated over the big size of the black hole and the long time of the black hole is so big that it has a measurable effect that black holes will have some temperature and will radiate like a black body. Okay, and when he gives this spoiler, before going into the details of this derivation, the derivation is the main part of the paper, he makes some comments about why this actually, how we could think of this, and how this fits with works that were done around the same time by Bekenstein. So I don't know if you guys were in last year's beautiful course, we spoke about Bekenstein, and Bekenstein had suggested that black holes have entropy. Okay, so let me briefly just say what Hawking said at this point. Any question here? So, okay, so Bekenstein had noticed an analogy between the second law of thermodynamics, which is du equal TdS plus some charge times the mechanical potential. Is this how I wrote? No, okay, in volume, okay, PdV. And Bekenstein and others have noticed an analogy between this and the laws of black holes that says that when I have a black hole, I get something like kappa over 2n d of area over 4 plus, if the black hole has angular momentum, omega dj. So this part we are not going to discuss today. But we have an analogy between these two terms, and Bekenstein and kappa is the surface gravity, which in the case of the black hole is m over 4 or 1 over 4m. Let me get it right. Sorry, 1 second. Where is it?
Should be getting right because of the transmission analysis.
Another 1 second. 1/4m, yeah. And so Bekenstein had suggested that the area of the black hole also always grows, and when we join two black holes, the area is bigger, so it looks like entropy that's always growing. And so Bekenstein had suggested that this term should be identified as some kind of entropy of the object. Now, the factor of 4, I'm cheating, I'm putting the factor of 4 here. Bekenstein did not know about the factor of 4. He said it's proportional to this. And then Bekenstein had also said that whatever multiplies this, he did not know about the 4, so there was some ambiguity, but he said this is some kind of temperature. This was Bekenstein. But he actually did not say it's a real temperature. He said we should not take this seriously. It's not a real temperature, it's some kind of temperature and so on. And Hawking says no, it's really a temperature. It's fine. It's not some kind of temperature. It's okay. It's a temperature, and we will see it's really a temperature. Okay. And then already in this first paper, which was a surprise for me. I thought this was some kind of popularization thing or so on, but no. Already in this paper, Hawking says, so how could it be that a black hole radiates, this black hole always absorbs? And then he gives this picture that everyone gives in popularization talks of the pair of particles that is created close to the horizon, and one falls inside and the other falls to infinity. So it's indeed mentioned in the paper. So he says that I have my black hole, and here what could happen is that one particle could escape if the other goes in. And he points out that this is actually possible because here d dt, this vector, becomes space-like. And so we could have a particle here with positive energy, and this particle here could have negative energy, and this would be totally fine, even though we start creating two time-like vectors. As one enters, it's negative, and so we could have conservation of energy with one particle reaching infinity with E bigger than 0, and one going inside and changing sign and becoming negative energy. And so what would happen is that because it's negative energy, it decreases the mass of the black hole, and therefore the black hole evaporates because it becomes smaller and smaller as it's getting energy outside. So the energy is outside, and this is energy negative, and so the mass as it's radiating is becoming m minus this small energy. And so the mass will decrease, and this will be the evaporation of the black hole. And actually, it's not a bad cartoon, because you see, how much does it change sign, this vector? This is related, this change of sign, by how much? Is related to this term f of r dt squared by how fast this term it changes at the horizon. But how fast this term vanishes at the horizon and how fast it changes sign is precisely the surface gravity. So it's really quantitatively true what he's saying. It's not just some blah blah. It's really precisely about how fast it changes here in the matter that is in fact governing the strength of this thermal radiation. Okay. Any questions? So that's the motivation, and and this the spoiler, black holes radiate. This is the temperature. That means Bekenstein. That's why it's called Bekenstein-Hawking temperature, because, and Bekenstein-Hawking entropy, because it was really together that they understood it's not just an analogy, it's really thermodynamics. And now he went on to do the computation. So first, let me remind you that the modern derivation of this temperature is what we did in the lecture of Bekenstein last year. So if you want to watch the 3-minute derivation, it's there. You can watch the video, it's much simpler. And now we do the 33-minute derivation instead. But the 3-minute one with path integral, much cleaner using Euclidean quantum field theory, it's done in the lecture last year. So, what is a black hole? The black hole is this. This is the Penrose diagram for the black hole. And we should compare it with the eternal black hole, whose Penrose diagram is this. Right? So this is Schwarzschild, the eternal black hole, a solution that exists always. And this would be a black hole formed by collapse, where I have some body that falls. So this would be some gravitational collapse, like a star. And spherical, so that this Penrose diagram is enough. Then this line here is the horizon. This is the singularity. And this is the origin of radial coordinates. Okay. And here, constant radius surfaces would be this. And in particular, this one would be R going to 2m, the horizon, which would be here. Okay. And so this is the eternal black hole. And this is what we care. Right? The eternal black hole is static, and we want really to have some background that is changing to study particle production in a background that is changing. Right? So now let's remember what the eternal black hole is. The eternal black hole, the metric, is equal to this function f of r dt squared plus dr squared over 1 minus 2m over r plus r squared d theta squared plus sine squared of theta d phi squared. And of course these factors, you see, they blow up at the horizon. The horizon is just a coordinate singularity. There's nothing special when I pass here, right? So if I'm passing here, I'm okay. No problem. It's just a coordinate singularity. But it is true that the metric vanishes here, so there are huge red shifts and blue shifts across the horizon. So things that are order 1 for someone here close to the horizon could become hugely redshifted and so on. And this is going to be very important. Okay? So even though, this fact that it vanishes, this leads to huge blue or red, depends on the point of view, shift effects. Right? So from outside, for example, if I throw something in, I see it slowing down and down and down and becoming and fading away. Right? So for me, everything fades away. So if I throw something like an atomic bomb, exploding, when it's reaching the horizon, it looks very faded away. Conversely, if I have something of order 1 that looks at order 1 at the horizon, I know that when it's coming to me, it's going to be very energetic. Okay, very good. So this is going to be quite important. And here, the metric is this, because we are outside. So outside the matter, we have this Birkhoff theorem or whatever, this Noether theorem, that you have a spherically symmetric metric and so on. There outside the metric is just Schwarzschild. But inside it's something complicated. Okay? And so here, inside the body, the metric is complicated. Okay. Good. Any question? So let's also set up the notation. Let's call this horizon H. This surface here where light rays end Scri plus. This where light rays come from Scri minus. This point at infinity, I0. Okay. Now, what's our task? Our task is to study some modes that start, say, without particles here. So I start with a field that only has some negative frequencies. And I ask, how does it evolve here? And when I look here, does it have positive and negative frequencies? That would be the analog of the oscillator. I start with an oscillator with only negative frequencies. But it evolves and the frequency changes, and that induces frequencies with another sign, and therefore I have positive frequencies now as well. Okay? So, good. So let's make that precise to see what we want to compute. Okay. So, we want to study in this geometry. Here, I'll put a massless scalar. So it obeys the equation box phi equals 0. Okay. One more comment. No, I'll do it later. It obeys the equation box phi equals 0. And then I can decompose my scalar phi, and I can say my scalar phi, I can decompose it as a sum of functions fi, this would be my operator that I'm quantizing, times some annihilation operator plus fi dagger times a fi conjugate times fi dagger. Where, this is important, where these fi's also obey box fi equals 0, they are the basis of solutions of Klein-Gordon, with incoming positive frequency at Scri minus. So at Scri minus here, I am basically in flat space. Right? I'm very far away from the black hole. I'm in flat space. I can define usual modes. And I will define the modes, this basis of modes, that when I go here, they look like the usual modes that I describe in flat space. Now, these same modes, when I evolve them and when I study what happens to them here, they are complicated, very complicated. This is just a boundary condition at minus infinity. So I define my boundary condition for these modes here. Okay? Because then, you see, so we will define this, and very important, our vacuum is the state 0 such that our state, the state we are in is the state 0 such that these oscillators kill the vacuum. In other words, I have no particles. No particles by assumption. at minus infinity. Okay? And then we will ask, how does this field evolve to the future? Again, in the future, I converge to a stationary solution. It's like this frequency. I'm again in a stationary solution, the black hole form. Again, I can define positive and negative frequencies. And I ask, if I start without any particles in the past, do I end up without any particles in the future or no? And we will see that no, we will end up with particles in the future. Okay? So this is my definition of my field phi, that I start without particles in the past. But then this same field can also be written, because it's just another choice of bases, so this same field, I can write it as the sum over I of pi bi plus pi bar pi dagger plus qi ci plus qi bar ci dagger, where now we have to explain what are these q's and p's, what are these functions. So these functions here, again, they always obey box pi equals 0 equal box qi. So they are also bases of functions that obey Klein-Gordon equation. But now they are defined in the following way. This pi is defined, so pi as positive frequency here and is 0 at the horizon. Okay, so this guy is 0 here, 0 here, and the derivative and the normal derivative as well. These two statements is the statement that there is no, it's what Hawking refers as no Cauchy data in H. So it has all the Cauchy data in this surface and its positive frequency there. Well, just one second. And Q's the other way around. Q are defined as having, this Q is defined as having 0 Cauchy data on scribe plus, and it's all on H. So together they define this Cauchy surface that goes from this point to this point. And from this Cauchy surface in the past, I can evolve to any Cauchy surface, such as this one or such as the final one. And therefore, modes that are decomposed in this past Cauchy surface can also be decomposed in any surface, in particular the last one, where again I have some definitions of my modes as positive and negative frequency modes. Here and here certainly, here not really, but I don't care, I pick any basis here, provided this basis is orthonormal, and now I have to define a scalar product to say what it is. Okay, so all this is well defined, but I didn't have time yet to say, plus, all this is true, plus, we normalize things, we normalize the Fi, the Pi, the Qi with the Klein-Gordon scalar product. Such that, for example, the scalar product between Fi and Fj is defined as I over 2 integral over the Cauchy surface. In this case, it's going to define it over S. But it doesn't matter which one it is, it's invariant. Over this surface S of Fi derivative of J bar minus J derivative of Fi. And this, we make it orthonormal, so this will be delta J. And similarly for the other fields. Okay? Now, this uniquely defines the modes Fi and Qi, Pi and Fi. It doesn't define the Q's because the Q's I did not explain what is positive and negative frequency here, but it doesn't matter. Pick any basis that's orthonormal, and this basis is not going to matter. We are going to consider only stuff that we measure here and here. This is like stuff that falls into the black hole. And so the physics is that is very important, is that this guy is about what comes out, whereas this guy is about what falls into the black hole. Right? It's about stuff that's falling versus stuff that's getting up. Okay? Good. So now you see that, yeah, so any question? There was a question here. Yeah, Jean?
So first, can you say again if box is defined on the curved background or flat space?
Box is in the curved space.
The curved space.
Curved space, yeah. So box phi is nabla A del A phi.
And how do you define the creation and annihilation operators in this different? So are you defining different vacua?
Different what?
Vacua at scribe minus and scribe plus.
No, the vacuum, our state is our state. It's this state. This state is characterized by being annihilated by these operators that we call A's. Now, this operator now, the next equation I'm going to write, is tell you that these operators B hat are a linear combination of the A's, or the A's are linear combination of the B's.
And what about C?
As well.
Okay.
That's all.
Thank you.
No problem. More?
Is it correct for me to say that you're assuming that in scribe minus and scribe plus you have a cyclically flat kind of space time? That's that.
No, not in scribe plus. In scribe minus, I have here some space. Here, the space looks flat here, but here it doesn't look flat. So here, it includes the region close to the black hole, and that region is important. But it's stationary. So here the metric is just eternal Schwarzschild. And here the metric is also eternal Schwarzschild, but moreover it's in practice flat. Except here, but here it's totally irrelevant. It's very early formation. It has no relevance for radiation. Yes?
I think you have already answered in the talk, but the Cauchy data is the data on the surface.
Cauchy data, when you say Cauchy data, means you give the function and the derivative. But
Okay.
what you need to evolve the
Cauchy
function.
boundary conditions. Okay. So is it okay? I don't know.
Being, it's what I said. When you say a function has no Cauchy data in H, it's a fancy way of saying the function is 0 and the normal derivative is 0.
Okay.
Any other question? Okay, so again, I have a field. This is a complete basis, so I can decompose it. This is also a complete basis, right? Because it's again a Cauchy surface, and I pick a full Cauchy surface and I decompose them all, so I can also decompose it. But because these are two complete bases, there is a relation, a change of bases between the two. I can write the p's as function of the x, or the x as function of the p's, and so on. Okay? So because these are just different bases, being just different bases, it follows that the pi, that these modes, are linear combinations alpha ij fj plus beta ij fj. Right? Because this is the solution of Klein-Gordon, this is the basis of solution, so I can derive this solution as a combination of these two. Okay? And same for Q. And now, if you plug this P and the same relation for Q there, and then you use the scalar product to extract the coefficients of Fi, that implies, okay, this is just plug plus use the Klein-Gordon scalar product. That implies relations such as this one, that Bi equal to alpha bar ij aj minus beta bar ij a dagger j. Okay, and similar for the other ones. Right? Is it okay? Moreover, the fact that it is just a change of bases, moreover, it also implies the following relation that we are going to use in a second, which is that if I have this matrix alpha times alpha dagger minus beta times beta dagger as matrices, that this is just the identity. Okay? This is just the fact that we can change bases. It's just a change between two orthonormal bases, so if you can easily see that this relation also follows.
What's the difference between alpha bar and
Sorry. Yeah. This is a matrix, so this means conjugate and transpose this matrix.
alpha? No, but on the line.
Here,
Components?
here I'm using components, here I'm using matrix. Right? So, is it clear?
Yeah.
Very good. Okay, so this is the equation we get, and therefore you see that if on our state that is killed by AI, right? BI, when I act on this state, this term is killed, but this one survives. Right? And therefore, we conclude that we see that the expectation value of BI dagger BI, how many particles I see in the future, is actually given by the sum over J of absolute value of B I J squared. Very important. And so the conclusion is that we just need to compute beta ij. Compute beta ij, we are done. Then we learn about how much particle production is there at infinity. But this just looks super complicated because this is a collapsing metric. How can I compute this? It looks very hard to do. So naively, this, you could say, seems super hard. The metric is simple asymptotically, but in the middle it's a complicated collapse. And Hawking points out that actually, no, it's not hard. You just need to think a little bit, but it's actually easy. And the details of the metric don't matter much. What matters is the asymptotic region. Okay? And the reason is because of this huge blue shift and red shift that will mean that all the interesting physics will happen here. And this physics that's happening here, there is a huge blue shift effect here. And because of this huge blue shift effect, when we enter this region, things are very complicated, but they are hugely blue shifted. So if you want to ask, I have some radiation that got to me that was order 1. Right? It was some radiation I measured in my thermometer. So then here, it's hugely blue shifted. So it's super hot. It's super high frequency, this radiation that I got that in my thermometer was like 20 degrees. Here it was super high frequency. And because it was super high frequency, if I want to trace this radiation, I can use geometric optics. I can use the fact that it's just a particle. When things move with super high frequency, they move just like a particle. And so even though I do this, I know that this just follows a geodesic. This is just geodesic. Okay? And because it's just a geodesic and I have here the picture, I just drew it. It's kind of done. Okay? So that's the moral of the story. So the reason is that it's just geodesic. And it's just geodesic because it is just geometric optics. And it is just geometric optics because of the huge blue shift. that's the moral of the story that will allow us to do the computation. Okay. Good. So let me write the result of this computation. But is there any question here? So these formulas are very important. So this stuff here is what nowadays people refer as Bogoliubov transformations. But Hawking never uses this way. But this kind of change of bases and the fact that because you have a change of bases, you have particle production, now everyone calls it just Bogoliubov and it's something more or less standard, but at the time it was kind of new. Any question here? Let me know if there any confusion. So again, I have my operator, it's decomposed in a basis. I can decompose in another basis using final operators. The fact that it's an orthonormal basis tells me that these coefficients of change of bases obey some simple relations, the generalization of unitary matrices or orthonormal matrices. Here it's like this minus sign comes because this scalar product has this minus sign. So if you work out, okay, it's just what it is. So there is this relation. And then because of that, I can just write a change of bases. And that change of bases, I can either implies that these operators B, they are related to the operators of annihilation and creation operator in a way that if I have no beta, then I have no particle production because this guy still kills the state. As soon as I have beta, I have particle production because this guy kills the state, but this one does not, and I have particle production. And this is the amount of particle production I have. Okay. So this is of course very general. It works in any space-time. We could apply to a space-time that, for example, is flat space. Then it grows a bit and it becomes flat space again, and you can use this and solve the differential equation and find out how much particle production you would have and use it for cosmology, for example. Okay? But we are using it for this collapsing geometry. Okay. And so all we need to do is find this coefficient, so find the change of basis, so find how a simple incoming wave behaves when I go to the future. Or conversely, I can start with a mode in the future and ask how does it behave when I go to the past. Okay? And so the claim is the following. Okay. Okay. So now let me just write first a short statement and then a few words about how to explain it. Okay, so the claim is the following. Take a mode that behaves as e to the minus I omega u here, and here is here. Okay, so at scri plus. Okay, what is u? U and v are the usual coordinates that we use. This Tortoise coordinate u minus r minus 2m log of r over 2m minus. And v is the same plus. Okay? So these are coordinates that are particularly nice to use in Schwarzschild because geodesics keep these coordinates constant. So incoming and outgoing geodesics are lines where u and v are constant respectively. Okay? So this u would be constant for a null outgoing geodesic. So if I draw a geodesic gamma here that reaches some point q, along this geodesic, this variable u would be constant. Okay, and so at infinity, this would be the analog of having a mode with some negative frequency mode. Is it okay? Okay. And then you ask, if I have this mode here, how does this same mode, I start with this boundary condition, how does it look like here in the beginning? Okay? And the claim is that this mode here behaves as follows. Now I'm going to tell you the following. We are interested, this region here is what we care. Right? We are here. Remember that this is the point infinity, right? So this is time equal infinity, any space. So asymptotically we all go to this region here. We are not here, right? We are in this region here. And so it's not surprising if you trace back geodesics that go to that region. You see they bounce, they pass by the origin, and they will accumulate close to this point. There is a point V0 that I can choose my coordinates to be 0. Plus some constant. And I can choose this coordinate V equals 0, and geodesics accumulate at this V. Things that I throw away after, they don't leave, they stay inside the black hole. Right? And so this V equals 0, this guy is matters. This is important. Right? It's the last point from which I can throw geodesics and they still get to infinity. Okay? And importantly, you see that this is a positive, this is the frequency mode, but U blows up when R goes to 2m. Right? So this U blows up as R goes to 2m. And therefore you can think that you have some frequency here, and this frequency effectively accumulates here close to R equal to 2m. Right? This variable is very fast. And so this is related to this huge blue shift. And because things accumulate here, if you follow them down, they accumulate here as well. You just follow down, and it means that here the modes will accumulate here like crazy. That's a reflect of this accumulation. And the fact that to follow them back, because of this huge redshift, I just follow the geodesics. And because of that, if they accumulate here, they accumulate here. And the claim is that they behave as follows. They behave as step function of minus v, because there's nothing after v equals 0. Right? And then exponential of I omega over this surface gravity k, 1 over 4m, times log of minus v. Okay, so that's the claim. Plus some constant times e to the minus I omega v. And this stuff we will call the interesting part that we call P2, and this the boring part that we call P1. We call it P because we are decomposing a mode P into two parts. One part is this, one part is this. So what is the logic here? The logic here, Hawking says, is the following. If I backtrack a field, two things can happen. The field can just reflect and go to infinity, or it can enter the body. Now, if it reflects, it's always moving outside the body. If it's always moving outside the body, the metric is stationary, because it's just Schwarzschild metric everywhere outside. And because it's stationary, the frequency doesn't change. And so those modes are kind of boring. It's like saying if I have a particle, okay, it could be out, it could just stay outside. That is, the field is just a particle that I throw and it doesn't, it just stays outside and goes from minus to plus infinity. Okay? And so the fact that it's the same frequency is because outside the metric is stationary. Whereas this stuff, you can think, no, this is the stuff that really got into the body and went back. Now, let me emphasize, it's not got into the black hole. The black hole, the horizon is here. Nothing is going into the black hole. This is always happening in our lecture. But it's getting inside this body, the metric here is complicated, and then getting out. Okay? Okay, good. So let's ignore this for now. Because this part is about alpha, not beta. This doesn't change creation and annihilation. So for now we'll ignore it and we care about beta. And so what we want to do is take this expression and ask, write this, so Fourier transform it, right? To see this as a linear combination of Fi's and Fi bars. Because the Fi are modes with definite frequency in the past. Okay? So there are two things we have to explain. The second one is this Fourier transform. The first one is why is this claim true? Okay? So again, this mode behaves like this. It's a statement. I have to say a few words why it is true. Now that we know that this is true, I should ask how does this decompose into the x? Because then when I see this decomposition, I learn about this alpha and beta. Alpha and beta are the decomposition of that mode into x and f naught. Okay, so there are two exercises, just doing a Fourier transform to read off alpha and beta, and explaining a little bit in more detail with geometric optics and so on. Okay. Any question here? Okay. So the point is the following, is that all we have to do is know that in geometric optics, the phase is constant along geodesics. So if you have an old geodesic, that is a line where the phase is constant. And so I just need to show that this phase, a particle that is in some location u, it follows this geodesic u, then it goes to some position, and I need to find what is that position v. So the claim is that starting with a u very close to u equal infinity will give me a v very close to v equals 0, and the map between u and v involves some logarithm, and that's why what was a u becomes a v. So this is just a statement identifying that this u, so this geodesic, will be this one, will give the map between the u and the v, where it comes from, involves an exponential map. So how do we follow geodesics? There is this standard treatment, which is that if you have an old geodesic, and you have another node geodesic, and you have another node geodesic here, a bunch of node geodesics, and if this geodesic is some distance epsilon, but by epsilon I mean that this geodesic here is affinely parameterized. Do you remember what this is? And you can write geodesics in any parameterization, but there is a nice one where it's affine. It's such that if this direction is v, I have something like v nabla derivative of v equal 0. Okay? So if this is such that you have your geodetic is affine parameterized, and if this distance in that affine parameter is epsilon, it remains epsilon all the time. And then all I have to do is follow what is the affine parameter for two nearby geodesics. And we know that in Schwarzschild, the metric we want to use here is this metric where I have this d capital U, d capital V times some f bar plus the two sphere. And this U variable is basically e to the minus kappa times U. And it's in these coordinates U and V that are very nice coordinates that Kruskal introduced, that you see the metric is totally regular around U equals 0 and V equals 0, which are the horizon. And this is the metric that allows you to see it's not a singularity, you can just pass by. And those coordinates are also nice because if you solve for null geodesics, indeed U equal constant is also geodesic, because I mean, when big U is a constant, small u is also a constant, so that's fine. But parameterizing in U or in V is better than in capital U or V are better because those are affine parameters. And so being a small distance away, being at a small distance in U away. Right? Whereas here, when I am in this region, the metric is just flat, so it is just the usual du dv without any exponential. And so a small distance here is just a small v, which is a small capital U, which is related by an exponential to the small u. And it's this crucial fact that puts the log here. Is it clear? So we just converted a fine parameter from one point to another. Any question? Okay, good. So now we can Fourier transform. What time is it?
12.
Sorry?
7 past 12.
7 past 12, okay. So now we Fourier transform. So let's define our function phi that is a function of omega prime and omega that I define as the integral e to the I omega prime v dv from minus infinity to plus infinity of this, where this is this. Which was what we called before P2. And so now I want to do this Fourier transform to see the decomposition of the modes. And the claim is the following. The claim is that this phi of omega and omega prime is equal to the alpha that we want of omega prime if omega and omega prime are both positive, and phi omega of minus omega prime would be the beta omega prime if again both are positive. Right? So that is, you have to follow carefully the signs to see, but it's straightforward to see. And so you want to compute this Fourier transform. When both are positive, this gives you the alpha. When one is positive, one is negative, this gives you the beta. But what is this integral? This integral is an integral from minus infinity all the way to 0, because there is a step function there. And so this integral is an integral where I integrate all the way to 0, and at 0 there is a cut. And so how do I compute this integral? I don't like this oscillation, so I move the contour here. But moving it here or here, I have to be careful. I can move it in one direction or the other. This depends on what? On the sign of omega prime. which direction I can rotate it to. And then after you rotate, what you will realize after you rotate, before even trying to do the integral, is that the final results are almost the same up to a phase. Because you get log of minus v, and if you rotate in one direction you pick I pi, in the other you pick minus I pi. Right? And because of that, without doing any computation, you can derive that this guy is just equal to minus e to the minus pi omega over kappa times phi of omega prime. This is very similar to the type of manipulations we did in Riemann's paper on the Riemann's hypothesis, where we were deforming some contours and picking some phases. And therefore, we conclude that the beta is thus proportional to the alpha up to some number. But on the other hand, I have this equation that tells me what the alphas and beta must satisfy. Okay? And so combining both, that just implies that the summation that this quantity is equal to 1 over e to the 2 pi omega I over kappa minus 1. And that is just the Boltzmann weight for a black body with a temperature that is given by kappa over 2 pi. So we just learned that the temperature is equal to kappa over 2 pi. And that's Hawking's temperature. Okay? Now, Hawking did it in a more complicated way, but got a better result because actually, as he points out, it's not 1, it's gamma. Because it's not really a perfect black body, it's a gray body. There is a factor that says it's not perfect. And why is it gamma? It's gamma because we ignored this guy. We ignored the stuff that just reflects back. Okay, and there is a bit of stuff that reflects back. So if you take into account this gamma comes from this P1. If you do the algebra carefully, there is a small shift in alpha and so on, and then you will get gamma. But the conclusion doesn't change. It's a body that is a gray body emitting at a given temperature. Okay? And so that is the conclusion, that we get a perfect thermal spectrum. This is nothing but a thermal spectrum you expect for a particle. If this is the energy, then this is the temperature. Okay? The inverse of the temperature. Right? This is beta. Okay? And again, and so it works. And the only thing that was important was really the behavior of the metric close to the horizon and the fact that there was this important exponential factor. This exponential factor is precisely the definition of the surface gravity, which is precisely related to how the metric vanishes there, which is precisely related to by how much the sign changes as I go there, which is related to this naive, this heuristic intuition that this is the mechanism for particle production that allows for particles to radiate, so it sounds reasonable. Okay? So let me just conclude. So what then? Okay, this is the main part of the paper. This part, by the way, I did not follow Hawking for this little bit. Hawking does it in a much more complicated way, but this trick here is very nicely explained in some lectures. So this trick here I learned in some lectures of Townsend. So it's some black hole lectures, which are very nice lectures. And it's chapter 7. So I recommend if you want to study this in more detail. And then Hawking goes on and says, okay, so what should I make of all this? And then comes the speculation part. Okay, so this is the solid part. Okay, everything we said is true, correct, and so on. And then he says, okay, so what is the correct picture for a black hole? Because the black hole eventually evaporates, so this picture cannot be correct. This is a black hole that stays there. And now we learn they have a temperature, and so they start radiating, eventually they disappear. And so he says, oh, perhaps in the end, after a very long time, perhaps the correct Penrose diagram is actually different. Perhaps it's something like this. And he draws this by now famous diagram, where he says there would be the usual singularity. There is here the origin of radial coordinates. But maybe what happens is that eventually the black hole radiates, and here we just have flat space again. Plus, of course, radiation that came from the black hole. And okay, that's of course the beginning of all this business of information puzzle and so on. That I started with something, I had some non-trivial state that I throw in, and I throw in all this stuff. And then I have totally mixed thermal state. And how can a nice pure state evolve into a pure thermal mixed state? And this is the information paradox. So then this is what people then are confused about still today. Right? So this is what's called the information paradox. Moreover, then he says, so what happened to all this stuff that was falling? I said, maybe it went to another universe. After doing all this careful computation with the fine parameters, maybe it went to another universe. And by the way, you see there are a lot of baryons here, and now there's only radiation. Maybe that's why we have so few baryons in the universe today. Maybe there were many, and they were all eaten by black holes and then evaporated. It's beautiful. The last page is really full of fantasy, and maybe some of it is true, but it's really, he deserves it after this beautiful computation, geometric optics and so on. Then go wild, man. But he did not save words there, and it's a beautiful last page. I recommend having a look at some wild possibilities, and I think the truth is that we don't know the answer to all these questions even today, so it's fine to speculate. It's okay. Okay, very good. I think we are good. Thank you. So, any questions or volunteers? And volunteers. Or volunteers and or questions. Yes? So you can volunteer for it's next Friday. Next Friday. Who else wants to volunteer? Thanks. Okay, so please coordinate with each other which papers you do and who goes first, and let me know the paper a few days before in case you are in doubt whether it's a good paper or not. Were you here in the previous lectures? I don't think so, not yet, right? So just someone could explain the format. But the basic idea is it should be a recent paper that refers to this paper. And the more recent it has, it can have less citations. But if it's from, say, it should be after 2000, say, and if it's a 2000 paper, it should have a few hundred citations. If it's a very recent paper, it's fine if it has 20 or 50 citations. This is a popular topic, so it needs to be really impactful. It's not like the previous ones, and this one. We should measure, it needs to be in the hundreds, probably, both of your papers, or thousands. Yeah. Everyone loves this. So. Okay, questions?
So, when you compare the frequencies, like you need to have some asymptotic state, right?
Mm-hmm.
In the past and in the future.
Yeah.
To compare. But imagine that I want to do the calculation in a space-time that does not have this asymptotic region, or if I want to know what an observer in a region that is not asymptotically flat will see from the radiation. Does this still apply, or I need to do something?
No, then you have to be more careful. So, if you have, for example, a flat space, and you want to ask what's happening in a very complicated region which is time dependent, there it's not really about particles, but you can consider some kind of energy operator and measure the average of the energy operator in some region to have an idea of how much energy is there. You have to think of a better experiments, right? The notion of particles is good when things are big, static, and so on. Right? Even if things are very small between two plates and you're discussing the effect and so on, particle is not a good description. It's better to use fields. So, not always. Sometimes it is. Sometimes you can still locally zoom in and see that the notion of particle is good, like I described in the beginning. And there you could ask an observer that is in some region, how many particles does this observer measure? And I should be careful that there is a limited detector resolution that they can use. If the frequency they are trying to detect is too small, they cannot do it because that requires an instrument to be bigger than the radius of curvature that they have access to. So they need to build an instrument that is inside some region. And because of that, they can only measure frequencies that are as small as some cutoff. But they can do it.
Yeah, I was reading a discussion by Pedro. He says that when you build a quantum field theory, you describe the vacuum and then you construct the whole space of states based on the vacuum, and you need an annihilation operator that kills the vacuum. But shouldn't like a consistent theory for applying curved spacetimes based on something that doesn't depend on the observer, or should be covariant in some sense, not like the vacuum state?
No, the vacuum state is crucial because here we said there's no particles here. But there is a different physical state, which is there is a radiation coming in. This is different physics, right? In one case, I see a collapse of matter and nothing else at minus infinity. In the other case, I see a collapse of matter and I decide to throw the radiation in as well. So that's a different state. And now I have particle production, but a different amount of particle production because I throw in some particle production as well. So that state is important. It's a different physics, it's different boundary conditions. So I think if you have some boundary conditions in your space-time, either asymptotically or at finite time, you will need boundary conditions. I don't see how to avoid it. You could say, could the boundary, then there are proposals like this no boundary proposal or something where things nucleate out of nothing and it's just a point, and then they grow and then it becomes big and now it evolves from there. Something like that, like for the Big Bang, for example. But that is, there's a hidden assumption there that you assume that things are regular and there are no particles at that singularity. There's always a hidden assumption. You are always putting in some boundary conditions, I feel. But that's a conceptual question. We can, in the end of the course, I can give a lecture about all the papers at the same time and we can discuss all the more philosophical stuff.
Okay, and you said that it's okay to do quantum field theory at curved space-time as long as the space is not shoe-curved. But if it becomes shoe-curved, then you would need to quantize space-time itself, like you would need a quantum space-time to do it.
We don't know what are the rules. We just know it breaks down. Maybe it's not space-time anymore, maybe it's something else.
Because
Like cavitation in water. You don't need a quantum water, you need molecules.
Okay.
But let me emphasize, the beauty of this computation is that there is a singularity here and we always stayed megaparsecs away from it.
Oh, okay.
So everything we did was totally under good control.
Okay.
I'm still confused on how you define your Hilbert space. For example, you define your Hilbert space space-like hypersurfaces that correspond to square I minus and square I plus.
Yeah, it's a bit not space-like, it's null.
It's null.
So it's a bit subtle because it's null. You can define it as a limit of a space-like surface, like this, but it's really an asymptotic limit.
But
So you could ask, are there subtleties about identifying what is the asymptotic region and so on? This is all this business of BMS symmetry that Hawking alludes to briefly. This asymptotic symmetry group of flat space and how to think of a null boundary. It's something that it's explained in the paper. You could be a bit worried about that, but the punchline is that you don't need to be.
Yeah, I was like wondering about the unitary equivalence between the two and the two asymptotic states in this case.
Yeah, for me, null is just what's the difference between null and space-like that's almost null. I would say there cannot be a difference. Null. Now space-like and time-like, yes, that could be totally different. No one knows what it means to.
But like some modes are absorbed by black holes, so like would the
this give us some guess on how is the structure of the Hilbert space? And
No. No, the structure is defined here asymptotically. I just have some modes. This is a complete basis.
okay,
There is some combination of modes that is complicated here that will eventually describe something falling in. But that's not my problem. I just define the modes here. Everything is smooth here. Everything is just asymptotic. And I have a complete Hilbert spaces. And that space of states is enough to describe everything that follows. Right? The Cauchy problem is well defined. You tell me, you give me something here, and I can evolve it no problem to the future. And you are right, some stuff falls in, some stuff goes there. I don't think there's anything conceptually wrong with that and problematic with that. Now, if you ask what happens here at the singularity, how do I treat this singularity and how do I quantize this, that we don't know.
would all the states that are contained in square I minus are contained in square I plus?
No, not everything. Stuff that is here will fall inside the black hole.
Okay.
So for example, we started with a mode here and we saw that decomposed here, it had support here. It didn't have support here. Right? There was this theta function of minus v. Right? So everything was supported here. Now what about here? No, here also you can get it because you can just reflect and go there. But that is the trivial, boring part. So most is localized here. So most of the stuff that you put here will fall in the black hole.
So the unitary equivalence is not trivial in this case.
I don't know what unitarity equivalence is. What is unitarity equivalence?
Well, you can go from one space, from the first Hilbert space to the another one in square I plus with a unitary transformation between the two.
If you are referring to these equations, they are written here, right? If I know the f's, I know the alphas and betas, I get the p's. If I know how my oscillators acted on the state, I know how they act in the state in the future. I don't know, what else do you want that's even better than this? Right?
Yeah.
From this, we learn about expectation values in the future, from expectation values in the past, fields in the future, from fields in the past. Just that the map is complicated a priori because it's a very complicated collapse. So physically what you expect is, if you try to build an experiment that is here in this region, by doing some kind of wave packets, that is not captured by what we did. Because this part is captured by some details of the collapse that are very non-universal. And then this blue shift is not huge, and then I cannot ignore the details of propagation, and nothing that we did is correct. But for the physics that happens asymptotically, which is what we care when we go to infinity to receive the radiation, there is this huge blue shift, we can do the computation, and there we have good control, and it's what I described.
Okay, so the problem is addressed somehow, like under
There is some non-universal part, which is natural, right? I mean, if you have a black hole collapsing, it's a big burst of energy collapsing. The details of that collapse will emit radiation as well. And those details, I cannot just compute in the black hole in 3 seconds. It depends on what type of matter, is it dust, is it radiation, what exactly it is. But the beauty of the computation is that asymptotically, however, those details are washed out. I don't care about these details, I care about only the behavior close to the horizon because of this huge blue shift. So, whether I throw in rocks or books or people or mesons, baryons, doesn't matter, it's washed out. For late times, for intermediate times, of course it will matter. Right? If I'm sending Christmas lights, I will see the radiation of Christmas lights, red and green and blinking at infinity. Right? But I see it, as I'm throwing this Christmas light, I see it here. When I'm here, I don't see it anymore, they already fell.
So all possible problems are addressed by the assumptions and it's everything okay?
For me, yes. There are people that write papers about this, claiming there are subtleties with this and that and so on. Today, there's an industry that there are people that do a live out of saying that there are subtleties here. I don't see them, but I don't see everything. I just described the paper, I did not describe the full field of quantum physics. Thank you. Can someone please take this upstairs to Tiago? João can do it. Thank you very much. See you next Friday for the student presentation, and then on Monday after for a Witten's paper on more